I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss very important numericals on harmonic oscillators. So before doing the numericals, first let us list down the formulae that we are going to use and also understand the concept very quickly. So whenever we are talking about a simple harmonic oscillator, so we are not considering any damping forces that are acting on the system. And the equation for a simple harmonic oscillator is given by d square x by dt square plus omega square x is equal to 0. So this is the expression for a simple harmonic oscillator. And here omega square represents the square of the angular frequency, which is given by k by m. Omega square is equal to k by m, where k represents the force constant, or we call it as a spring constant here. If you are taking a spring, mass of spring constant, and m represents the mass. So omega square is equal to k by m. Now if we have to calculate the angular frequency omega, we have the formula 2 pi by t. 2 pi is the angle through which it's turning, and capital T here denotes the time period. Now if we have to calculate the velocity, now how do we get to the expression for displacement here? So the displacement here is given by y is equal to a sine omega t minus kx is the general expression we are going to take. And when we have derived the expressions for velocity, we have got v is equal to omega under root a square minus y square. This gives the expression for velocity. So wherever we need velocity, we are going to use the formula v is equal to omega under root a square minus y square. So omega represents the angular frequency, and capital A here is the amplitude. A is amplitude and y is the displacement. What is amplitude here? Amplitude is the maximum displacement. Now whenever we have to find the maximum velocity, V max if we have to find, so V max will be at y is equal to 0. So the condition for V max is y is equal to 0. So in this, if we put y is equal to 0, we have omega under root a square. That gives us, for V max we get omega. So that is what we are writing here. V max is equal to a omega. Now the next comes the acceleration. So if you see the expression for acceleration, so acceleration is given by omega square a. Or if I write not maximum acceleration, it is y. So acceleration is maximum. Acceleration is maximum at extreme position. At extreme means when the displacement is maximum, that is equal to amplitude. So when y is equal to a, the acceleration is maximum. So we get acceleration given by omega square a. Acceleration maximum. I say it is a max, or acceleration maximum is given by omega square a. So a max is equal to omega square a. So how do we understand this for a simple pendulum? Suppose we take simple pendulum as the simplest example of a simple harmonic oscillator. So now we have a simple pendulum, a small bob which is attached to a string and suspended from a rigid support. Now when you displace it to one end and leave it, so it keeps on oscillating. So this is one complete oscillation. It will start from here it will go and come back. From the initial position, I can say this is one oscillation. Now at the mean position, this is at y is equal to 0, the velocity is maximum. And at this position, the velocity will become 0. Now at the extreme position, that is at y is equal to a, the acceleration is maximum. So always these two conditions we have to remember. So when the displacement is 0, that is at the mean position, the velocity is maximum. And at the extreme position, the velocity is 0. But when you compare with the acceleration, here the acceleration is maximum at the extreme position. So A max is omega square A and V max is A omega. Now coming to damped harmonic oscillators. So what are damped harmonic oscillators? We have to consider the damping that occurs on the system. That is the resistive forces that act on the system to bring them to equilibrium. So what is the expression for a damped harmonic oscillator given by d square x by dt square plus gamma by m into dx by dt plus k by m into x is equal to 0. So this is what we have for a harmonic oscillator. Gamma is due to the damping and k is the spring constant. So we are also substituting the constants. So what we write for gamma by m is 2b. Substituting, instead of two constants, we are going to put a constant 2b. And k by m is given by the square of the angular frequency. So we write it as simply d square x by dt square plus 2b into dx by dt plus omega square x is equal to 0. So this is the expression we are going to consider for damped harmonic oscillators. So omega square is equal to k by m, which we have already seen. And the second one, b is equal to gamma by 2m. So if you are writing gamma by m is equal to 2b, so b will be equal to gamma by 2m. So in most of the cases for b, we are going to substitute gamma by 2m. And the time period t is given by 2 pi under root omega square minus b square. Now, depending on these values of omega square and b square, we have three conditions for damping. So what are the three conditions for damping we have? First one is we have under damping. So what is under damping? When b square is less than omega square. When b square is less than omega square, there will be under damping and the system will oscillate and then it will gradually come to rest. So only in case of under damping, there will be oscillations. So the system will be oscillatory. If you have to check whether, depending upon the conditions, whether the system is oscillatory or not, we need to check for this condition. B square, whether it is less than or greater than or equal. So what is it for critical damping? What is the condition for critical damping? So for critical damping, b square should be equal to omega square. So in critical damping, the system is not oscillatory, but it will rapidly come to rest. Quickly it will come to rest. And the third case is for over damping. So what is over damping? If b square is greater than omega square. So in both the cases, the system is not oscillatory. The system is not oscillatory in both the cases. Only in the first case, the system oscillates and comes to rest. In critical damping, it comes to rest fast, but here it comes to rest slowly. Now the next one is forced harmonic oscillators. Now because of the damping, the system may eventually come to rest with oscillating or without oscillating, depending upon the damping. Now, if we have to sustain the oscillations, we have to apply some external periodic force. then it becomes a forced harmonic oscillator. Now, what is the expression for forced harmonic oscillator? So, we have d square x by dt square plus gamma by m into dx by dt plus k by m into x will be equal to f naught by m sine pt. Here this represents f naught sine pt represents the external periodic force whose frequency is given by p. And again we have seen the same substitution. For gamma by m we will write 2b. So this will imply b is equal to gamma upon 2m, and omega square is k by m, and we also write f naught, small f naught is equal to capital F naught upon m. So these are the equations for forced harmonic oscillators. So f naught is equal to small f naught, because capital F naught is a constant, m is a constant for a given system, so we can write one constant, that is f naught, small f naught. And the amplitude of vibration here is given by f naught upon omega naught square minus p square plus 4b square p square. So what is b we have seen? P here is the frequency of the external periodic force. Omega naught is the initial angular frequency. Then the phase is given by, or the state of vibration is given by tan inverse 2bp by omega naught square minus p square. So we have these two expressions which we'll be using to calculate the amplitude and the phase. So let us now move on to the numericals. Calculate the amplitude, angular frequency, time period and initial phase for the simple harmonic oscillation, which is given by y is equal to 0.3 sine 40 pi t plus 1.1. So it is understood that we have to calculate all these things. So for that, what we do is, we will try to write the general expression or the formula for y. The displacement of the particle in simple harmonic oscillation is given by y is equal to a sine omega t plus 1. So this is the general expression where y represents the displacement, a represents the amplitude, omega is the angular frequency, t is of course the time, at any instant of time we calculate, and phi is the initial phase. Phi represents the initial phase. So we have to calculate the amplitude, we have to calculate the angular frequency, we have to calculate time period also, not the time, we have to calculate the time period. Time period means the time taken for one complete vibration, we call it as time period, and also the initial phase. So we will try to write the equation here and try to compare the two expressions. What is given for us is this equation. So let us try to compare. A, in place of A we have 0.3. So the amplitude A is equal to 0.3 units. So whether if it is given in meters, the SI system will write it in meters. If it is in CGS, we'll write it in centimeters. So here I'll write it in units. Amplitude is 0.3 units. Now in place of omega, what is omega here? It is the angular frequency. So for omega, we have 40 pi. So the angular frequency is given by 40 pi, in radians we write. And in case of phi, that is the initial phase, phi is equal to 1.1. So we have got amplitude, angular frequency and also phi. Now we will calculate the frequency and the time period also. So we know T is equal to 2 pi upon omega, because omega is equal to 2 pi by T. So T is equal to 2 pi by omega. So we'll write 2 pi upon, what is it we got for omega? 40 pi. So this will get cancelled. T will be equal to 1 by 20. That is nothing but 0.05 seconds. So the time period we get is 0.05 seconds. So once you get the time period, you can find the frequency. F is equal to 1 upon T. So 1 upon T will be 20 by 1. So 20 Hertz is the frequency. So we have got amplitude 0.3 units, the angular frequency 40 pi radians, and the frequency 20 Hertz, time period 0.05 seconds, and the phase as 1.1. So that is how, with the help of the standard equation, while comparing, we can get the values. Now coming to the second one. What is the period of oscillation of a mass of 40 kilograms on a spring with a spring constant K is equal to 10 Newton per meter? So first we'll write the data. What is given we'll write, and then we will find out. We are given the mass as 40 kgs. We are also given the value of K, 10 Newton per meter. We have to find the period of oscillation. So there are two methods in which we can do this. Okay. So what is the formula we have for omega? Because we are given M and K, we can very easily calculate omega. So omega is equal to under root K upon M. So what is the value of K? 10. What is the value of M? 40. Both are in the same system. Otherwise, we need to check the system. Or if they are not, we need to convert it into the same system of units. So under root 1 by 4. So that will be 1 by 2. So once you get omega, we can calculate time period. T is equal to 2 pi by omega. Because we have to calculate the period of oscillation, that is time period. T is equal to 2 pi by omega. So 2 pi upon 1 by 2. So I can write it as 4 pi. 4 pi seconds. Or I can write it as 4 into, for pi 3.14. So 12.56 seconds. Or the other method is to use the formula directly for the time period. T is equal to 2 pi under root M by K. This is the direct formula we have for time period. So T is equal to 2 pi under root M is 40 and K is 10. So this will go 4 times. So under root 4 is 2. So 2 pi into 2. That gives us 4 pi. The same thing. So this is also 12.56 seconds. So you use any method. You start from the standard formula for omega and then get T. Otherwise, we can directly use the formula for T and write 2 pi under root M by K. Now the third one. A 4 kg mass attached to a spring is observed to oscillate with a period of 2 seconds. So the period is given, time period is given. What is the period of oscillation for a 6 kg mass attached to the spring? So write the data given first. M1 is equal to 4 kg. and the time period corresponding to this mass is 2 seconds. So what is the period of oscillation if a 6 kg mass? So M2 is equal to 6 kg. We have to find the period of oscillation T2. What is T2? So what is the formula we are going to use? Just now we have seen the formula for the time period. T is equal to 2 pi under root m by k. Here the mass varies, the time period varies, but the spring constant remains the same. So let us write the formula. T1 will be equal to 2 pi under root m1 by k. T2 will be 2 pi under root m2 by k. Because we want to find T2, I will take the ratio of these two. T2 by T1 will be equal to 2 pi under root m2 by k into 1 by 2 pi under root k by m1. 2 pi will get cancelled. Root k will get cancelled. So what we have now is T2 by T1 will be equal to under root m2 by m. So this implies T2 will be T1 under root m2 by m. Now we have mere substitution. We know T1, we know m2 and we know m1. So it is just substitution. So T1 is 2 seconds, under root m2 is 6 and m1 is 4. So 6 by 4 we have 3 by 2. So this will be 2 under root 1.5. So this will give us 2.449 seconds. So the time period when the mass varies, the time period varies. So what is happening to the time period with the increase in mass? So it is decreasing. Now the fourth one. A particle executes a simple harmonic motion of period 10 seconds. So the time period is given as 10 seconds. And the amplitude is 1.5 meters. Amplitude is 1.5 meter. We have to calculate the maximum acceleration and maximum velocity. So what we'll do, first write the data given. What is the data given? The time period is given, t seconds. The amplitude is given 1.5 meters. We have to find A max and V max. So this is what is given in the data. So what is the formula we are going to use? First we have to find omega. Because to find A max and V max, what is the formula for V max? V max is equal to A omega. And A max is equal to omega square A. So A is given, but we have to first find omega. No, in both the cases, for V max as well as A max, we need omega. Omega is the angular frequency, which is given by 2 pi by t. We are going to use this formula because the time period is given. So let us first find omega. So omega is equal to 2 pi by t. So substitute for t, 10 seconds. So 2 into 3.14 by 10, 6.28 upon 10 will give us 0.628 radian per second. So the angular frequency we are getting. Now let us find A max. We are finding V max first. So V max is A omega, A into omega. So what is the value of A? 1.5 meter. So 1.5 into omega we have got 0.628. So substitute for omega 0.628. So multiply. You can use your calculator to do the multiplication. What you get is 0.942 meters per second. So this is the maximum velocity. Now what is A max? Acceleration maximum is given by omega square A. That is the formula. Omega square A. So the square of omega 0.628 square multiplied by 1.5. That gives us 0.591 meter per second square. So the unit for velocity here is meter per second. Very important to note down the units also. And for acceleration it is 0.591 meters per second square. So we have got the maximum acceleration and also the maximum velocity. Let us see the next one, fifth one. A body executing simple harmonic motion has its velocity 16 centimeter per second when passing through the center mean position. If it goes 1 centimeter on either side of the position, calculate the time period. So first let us understand the numerical, what is given and what we have to find. So a body executing simple harmonic motion. So I'll take the simplest example of the simple pendulum. So we have a bob attached to a string and this is tied to a fixed support. When we take it to one end and leave, it starts oscillating like this. This is one oscillation. So this is the mean position or the equilibrium position. So we know that at the mean position, the velocity is maximum. We have already discussed this in the theory. And at the extreme position, the velocity is 0. And we also know the maximum displacement from the mean position, we call it as amplitude. So these three things we need to know. So the velocity is maximum at the mean position and the maximum displacement from the mean position, we are calling it as amplitude. So what is given here? The velocity is 16 centimeter per second when it is passing through the mean position. So I can consider this velocity as the maximum velocity. So Vmax is 16 centimeter per second. And then it goes 1 centimeter on either side. So here also it is going 1 centimeter and here also it is going 1 centimeter. That is the maximum displacement it is having. So I can write 1 centimeter as the amplitude. So given the velocity, maximum velocity and amplitude, we have to find the time period. So let us now do the numerical. First write the data. So what is given? We are considering the Vmax. Why Vmax? Because it is at the center position, it is maximum 16 centimeter per second. See here the units are in CGS system. So if all the given quantities are in CGS, we can continue doing the numerical in CGS system. Only if they are mixed, means one quantity is in SI system and the other is in CGS, we may have to convert into the same system and do the numerical. So here we will try to continue in the same system, that is CGS system. So what is the amplitude given by 1 centimeter and we have to find the time period. So what is the formula we have for time period? Omega is equal to 2 pi upon t. So t will be 2 pi by omega. So to find the time period, first we need to calculate omega. So how do we get the value of omega? We know Vmax is equal to A omega. So omega will be Vmax upon A. So from this formula we are writing for omega. Because we know Vmax, we know A. So let us first get omega. So omega is Vmax upon A, that is 16 upon 1. So that is 16 radian per second. That is the angular frequency. So once we get omega, we can easily calculate the time period. So time period t is equal to 2 pi by omega. So pi is 3.14 and omega we got 16. So 2 into 3.14 by 16, that is 0.3925 seconds. So the time period here means the time taken for one complete vibration is 0.3925 seconds. Now let us come to the sixth one. A body of mass 5 grams is subjected to an elastic force The elastic force is given. It is 40 dyne per centimeter. And then a frictional force of 5 dyne second per centimeter acts on it. If it is displaced through 2 centimeters, the displacement x here is 2 centimeter and released. What we have to find is whether the resulting motion is oscillatory or not. What is the type of motion it has, and also find the time period. So now, because we have the frictional force also, we have the elastic force also, so we will be considering it as a damped harmonic oscillator. So in damped harmonic oscillator, we have to check for the condition. We have already seen the equation and we have also seen the conditions. Only in the first condition, that is in underdamping, when b square is less than omega square, only in that case the system will be oscillator. So we will check for that condition whether it is oscillatory or not. Then we'll use the formula for time period. So let us write the data. So m is given 5 grams. K, the force constant, elastic force, is given as 40 dyne per centimeter. And the frictional force gamma, here I'll call it as a resistive force or the damping force, is 5 dyne second per centimeter. And the displacement is 2 centimeter. You have to find the time period. And again, you see all the quantities are in CGS system. So we'll try to continue doing the numerical in CGS without any conversions. So the formula we are going to use is, because we have to find the time period, T is equal to 2 pi under root omega square minus b square. So omega is 2 pi upon T and b is given by gamma upon 2m. So we'll write the formula for omega square is k by m and b is gamma by 2m. So let us first find omega square. Because we know k, we know m. So what is k? 40. What is m? 5. So 40 by 5 is 8. So omega square is equal to 8. Because we want omega square, we don't need omega. So we'll first find omega square. Next is b. b is gamma by 2m. Gamma is what? 5 and 2 into m is 5. So 5 by 10, that is 0.5. We want b square. So b square will be 0.25. So once we get b square and omega square, we will first check for this, whether the system is oscillatory or not. So what is the condition for oscillatory? So it is b square should be less than omega square, only then it is oscillatory. So what is the value of b square? 0.25. This is b square. And what is the value of omega square? 8. So obviously b square is less than omega square. So it is oscillator. Because we have to check whether it is oscillatory or not. If this condition is not satisfied, then it is not oscillator. Because this condition b square is less than omega square is satisfied, we are saying that the system is oscillatory. And now calculate the time period. So for time period, we have 2 pi under root omega square minus b square. So 2 into 3.14 upon root omega square is 8. Omega square is 8. So for omega square, I am directly substituting 8. And for b square, we got 0.25. So we are substituting 0.25. So 6.28 under root 8 minus 0.25, you get 2.25 seconds. So this will be the time period of the motion. Now let us see the 7th one. A 0.5 kg mass suspended from a linear spring of force constant 1000 Newton per meter. So the force constant is given here. And a damping coefficient of 0.05 Newton second per meter, that is given. And an external force F is equal to F naught sine PT is applied, where F naught is 25 Newton. And P is twice the natural frequency. P is the periodic frequency, external periodic frequency. This external periodic frequency is equal to twice the natural frequency. Then what we have to calculate? The amplitude and also the phase. So this clearly, the data clearly shows that it is a forced harmonic oscillator. So we have already discussed the equation and how to calculate the amplitude and phase for a forced harmonic oscillator. So we will apply the same concept here. So what is the data given? The mass is given 0.5 kg. Force constant is given 1000 Newton per meter. The damping coefficient is given 0.05 Newton second per meter. And F naught is given 25 Newton. And it is mentioned that the external periodic force P is equal to twice the natural frequency. So if I'm considering omega naught as the natural frequency, so P is equal to 2 omega naught. We have to find the amplitude A and the phase phi. So first write the formula. So formula for A is F naught. So what is F naught? Capital F naught upon M. We are given F naught and we have M. Upon under root omega square minus P square plus 4B square P square. This is the formula to calculate the amplitude. Now, first we need to calculate F naught. So what is F naught? Given by capital F naught upon M. So you have F naught, you have M. So you can easily calculate F naught. Then we need omega naught. So omega naught square is equal to K by M. We also have the value of K. So we can easily calculate omega naught square because we want omega naught square here. And the next thing is B. So B is equal to gamma by 2M. So gamma is given. So we can substitute and get the value of B. So once we get omega naught square, B and F naught, we can substitute in the formula for amplitude and get the value of A. So let us get omega naught square. Omega naught square is K by M. So that is 1000 upon 0.5. That gives us 2000. So omega naught square is 2000. Next is B. B is gamma upon 2M. What is the value of gamma? 0.05 upon 2 into M, 0.5. So what we get is 0.05. So omega naught square and B. Now we will substitute for F naught. F naught by M. What is F naught? 25. F naught is 25 Newton. And all the quantities here are in the SI system. So we are continuing the same system. So 25 by 0.5, this will give us 50. So find the amplitude. A is equal to F naught under root omega naught square minus P square plus 4B square P square. So what is omega naught square? Is 2000. So we have put 2000. And what is P? P is twice omega naught. So P square will be 4 omega naught square. We want the value of P square here, no? So how do we get P square? P is 2 omega naught, that is given in the data. So P square will be 4 omega naught square and we have got omega naught square as 2000. So P square will be 8000. So we have substituted for P square as 8000 square plus 4 into B square. So whatever we got, B 0.05. So B square will be 0.25 into 0.25. That will be 0.0025 into 8000. So when you simplify, you get the amplitude as 0.0083 meter. Now, after amplitude, we need to calculate the phase. So what is the formula for phase? Phi is equal to tan inverse 2 BP by omega naught square minus T square. So this is the formula for calculating the phase. So it is simple because we have all the values ready. We have got omega naught square, we have got P square, we have got P. Now it is just substitution. So what we have here is minus 4 into 0.05 upon 3 into under root 2000. Now, when we are substituting for p square as 2 omega naught, so it will be 4 omega naught square. And for p, we are substituting 2 omega naught. So 2b omega naught upon 3 omega naught square. So omega 1 omega will get cancelled. So we are getting 4 into b upon 3 into under root 2000, which gives us 0.085. So the phase changes by 0.085. Now the next one, a body executes simple harmonic motion such that its velocity at the mean position is 1 meter per second and acceleration at one of the extremities is 1.57 meter per second square. Calculate the time period of vibration. So first I'll write the data. So the velocity at the mean position, we have already discussed. So the velocity at the mean position is always the maximum velocity. So V max is 1 meter per second. And acceleration is at the extreme position. So at the extreme position, the acceleration is maximum. So A max is 1.57 meter per second. We have to find the time period. So what are the formulae we have for time period? T is equal to 2 pi upon omega. This is the formula. We are not given the value of omega. So we have to deduce the value of omega from these two. So what is the formula for V max we have? V max is equal to omega A. And A max is equal to omega square. So if I take A max upon V max, maximum value of acceleration upon maximum value of velocity, we get omega square A upon omega A, which gives us the value of omega. So if I want omega, simply I will do A max value upon V max value. So what is our A max? 1.57. What is our V max? 1. So our omega is now 1.57 radian per second. So once we get omega, we can clearly substitute it here. 2 into 3.14 upon 1.57. So this will go 2 times 2 into 2, 4 seconds. So the time period is 4 seconds. Now the next one. A mass of 2 kg oscillating on a spring with constant 4 Newton per meter passes through its equilibrium point with a velocity of 8 meter per second. What is the energy of the system at this point? Here again we need to understand. So we are talking about a spring whose mass is 2 kg. We'll write the data first. Mass is 2 kg and the spring constant K is 4 Newton per meter, and when it passes through the equilibrium point, its velocity is 8 meter per second. So at the equilibrium position, the velocity is maximum. So I will directly write V max is 8 meter per second. So what we have to find is the energy of the system. Energy is equal to what? Now what is the formula for energy or the total energy? For the total energy, we have the formula half kx square, which is the potential energy, plus half mv square, which is the kinetic energy. So we have to find the energy of the system at this point. What point? Equilibrium point. So find the energy of the system at equilibrium point. So at equilibrium point, x is equal to 0. So the whole term will vanish and we have only half mv square. Okay. So now we will just substitute for the mass we have 2 and for the velocity maximum it is 8. So into 8 square. 2 will get cancelled. 8 square will be 64. So the energy is 64 joules. So the energy at the equilibrium position, because we have seen in theory, whenever we are talking about an oscillator, the energy of the system is always conserved, because at the mean position, if the velocity is maximum, it is kinetic energy and the potential energy is 0. But when it goes to the extreme position, the potential energy is maximum and the kinetic energy becomes 0 because the velocity becomes 0. So to understand this concept, we are trying to do this numerical. So what we understand here is, because at the equilibrium position the displacement is 0, the potential energy is 0 and the total energy is due to the kinetic energy, that is 64 joules. Now one more problem. The periodic time of a body executing simple harmonic motion is 2 seconds. After how much time interval from t is equal to 0 will its displacement be half the amplitude? It's a very simple problem, but we need to understand the data given. So let us write the data. The periodic time, we write it as time period, is 2 seconds. So after how much time interval from t is equal to 0? Means we'll consider the initial phase to be 0. Will its displacement be half the amplitude? The displacement is half the amplitude, a by 2. After what time? That is what they're asking. After what time will the displacement become half the amplitude? That is what we have to find. So we will use the equation or equation for displacement. Y is equal to a sine omega t plus phi. But phi initial phase we have considered as 0 because it is starting from t is equal to 0. So I will simply write y is equal to a sine omega. For omega, I will write 2 pi by t. Because we are not given the value of omega, but we are given the time period into t. So what they are asking here is, at what time the displacement will become half the amplitude. So for y, I will substitute a by 2. A by 2 is equal to a sine 2 pi by 2. Time period is given as 2 seconds into t. 2 will get cancelled, a and a will get cancelled. So we have half is equal to sine pi t. So when will the value of sine be equal to half, or I can write it as pi t is equal to sine inverse of half or sine inverse of 0.5. So that is 30 degree. So sine 30 is equal to half, no? So sine inverse of 0.5 is 30. So I want to find t. So I'll write 30 as pi by 6. 180 by 6 is 30 into 1 by pi. Because I have to find t, I'm bringing pi onto the other side. And instead of 30, we have written pi by 6. So pi and pi will get cancelled. So we have 1 by 6 seconds. So the time, at what time means after 1 by 6 seconds, the amplitude, the displacement will be half that of the amplitude. So for more numericals, you can refer to engineering physics, or you can also refer to Cengage publications by Vijay Krishna and Harbola. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.